Okay, let's practice another proof. I'm going to give you a definition. This is the definition of divides. Okay, so the definition: if a and b are integers, we say a divides b, and we write it like this. Okay, a divides b if b equals a times c for some integer c. Okay, that's what it means to say that a divides b. It means that a times some integer will equal b. Okay, now here's a proposition. We are going to show that division is transitive. Okay, which is this: that a, b, and c be integers if a divides b and b divides c, then a divides c. Okay, so let's prove that. Okay, so let's start out at the beginning. Let a, b, and c be integers, and suppose a divides b and b divides c. Now, just so that you know, that could have been two lines. I could have done this. Imagine a capital S on the word suppose. Okay, I could have done that. But this is all part of the hypotheses. So it makes sense to me to put them in one line. It's up to you though. Okay, now that's where I'm starting with. That's what I'm given. What do I want to prove? I want to prove a divides c. So my goal is to work my way down and to be able to say, therefore, a divides c. Okay, and we'll give a reasoning for that when we get there. Okay, now how am I going to show that a divides c? Well, the only thing I have to go by is the definition of divides. So I'm going to show that a divides c by showing that c equals a times an integer. Do you agree with that? The penultimate line, which means the one before the last, is going to be saying that c equals a times an integer. Do you agree that that's what I need to get to? And then once I get there, then this will be automatic. I'll be able to say a divides c because I will have shown that a fits the definition of dividing c. Okay, so how am I going to get to c equals a times an integer? Let me write it like this: a times integer. How am I going to do that? Well, let's go back to the top and try working our way down towards that. Okay, what do I have to work with? I have that A divides B, and I also have that B divides C, and I know what it means for one number to divide another, right? So since we have A divides B, let's write down what that gives us. Okay, so then what's that mean? It means that B equals A times some integer. Now I can't use C here because C is being used for something else already. So pick another letter. How about we'll just go with D. Okay, so because A divides B, then B equals A, D for some integer D. Okay, and we might as well go ahead and say as well that what does C equal? C equals B times some integer, right? What do you want to call it? You want to call it E? And what is my reasoning for saying that? Because A divides B and B divides C, and that's what the word divides means. So I'm going to write by the definition of divides. Okay? All right. Now, you got to be a little bit creative here. You can't always just follow the breadcrumbs without thinking of where you're going, because there's almost never enough breadcrumbs to lead you all the way. So you have to be also creative, and you got to think about how am I going to get from point A to point B. Okay, so how are we going to get from where we just left off down to here? It's not a difficult guess to make. What do I know? I know that C equals B times E, and also I know that B equals A times D. So can't I just take that and substitute it in for B right there? And then what will I have? I'll have C equals A times D times E, correct? So let's say hence C equals, so I'm going to substitute AD in place of B. And then I'm going to use the associative property to write that as, instead of AD times E, I'm going to write A times DE. Isn't that exactly what I was wanting? I just have to point out what? I have to point out something about this. In order for me to be finishing my proof, DE needs to be what kind of number? It needs to be an integer. Let me ask you a question. Is it an integer? Yes, it is, because D is an integer and E is an integer. And an integer times an integer is an integer. So DE is, in fact, an integer, but it's my job, though, to point that out. I can't just say, oh, yeah, it is true. No, I got to say it. I got to put that in writing, okay? So I'm going to say where DE, not D comma E, but the number DE is an integer. Okay. I suppose I'm just trying to think back. That's why you're probably wondering why I paused. I'm trying to think back to the previous example that I did, and I'm just trying to give you. I want to give you some different views here. Okay, I could, if you don't like the way this looks, DE is an element of the integers. Here's what you could do. Give DE its own name. What do you want to call it? Should we call it F? So then I could say this. Thus, here, I'm going to take that off of there. And I can say thus C equals AF, where F equals DE, which is an integer. If you prefer that, that's fine. Okay. And then we have our conclusion. Therefore, A divides C. And why is that? What am I basing that conclusion on? I'm basing it upon the previous line and the definition of what? The definition of the word divides. Why did I not write a reasoning down for these two lines, since I wrote a reasoning down for these two? Why did I not for the two in the middle? Because what did I do in the two in the middle? I just used in this line here, I just used 9th grade algebra, right? I used substitution to substitute AD in place of B. Because of this allowed me to do that. And then I used the associative property to shift the parentheses over. That's all. You don't have to write down by substitution and the associative property. That is taking it a little bit too far, being a little bit too trivial. Okay, I said this last time. You don't have to verify your use of the commutative property and the distributive property and the associative property. All that basic 9th grade algebra stuff is 9th grade algebra. Okay, you don't need to give justification for your basic algebra steps. How come I didn't give a justification for this? Because I didn't really do any math here. All I did was just renamed the number DE and gave it a name that is a single letter. And besides that, remember I told you that you don't even have to have this line if you wrote the previous line the way I did before. If you have this at the end of the previous line, then you don't even need the next line to be written. Okay? So what I circled there, C equals AF, that's simply giving DE a name of the single letter F. And what else have I done in that line? Pointed out that that is an integer. Okay? Why is DE an integer? Because D and E are both integers, and when you multiply two integers together, you have an integer. That's called the closure property of the integers. And if this was an abstract algebra class, I forgot what number that class is, then maybe I would write that down. But I just, I'm just being honest with you. I don't think it's necessary to point out here that an integer times an integer is an integer. You're going to have to learn what needs to be pointed out and what does not require being pointed out. And an awful lot of that has to do with the setting. What is it that you're trying to prove? And what is your audience? If I was trying to prove this for a 9th grade class, then I would have pointed out my use of the associative property and the substitution property. I'm not pointing it out here because you guys aren't in ninth grade. You see what I'm saying? I hope that's not too vague, but these are some things that you have to get a feel for, and you have to decide. It's better if you're not sure. It's better to give more justification and have more than you need than not enough. Okay? All right, let's see what's next in the book. You can see this proof in the book too, and you'll see it's almost exactly like I've done it. They've used some different words, like the word likewise, and instead of using F for D times E, they've used the letter X. That doesn't make any difference. Okay, let's do this one. You're going to have to remember the definition of even and odd. So if you don't remember that, look at the last lecture and look that up. Okay. If x is an even integer, then, by the way, before I go any further, just so you know, when we use the word even and odd, those words only apply to integers. So I could say if x is even, that would be okay. That means, the word even means even integer when you see it. You don't have to say even integer. You can just say even, because that includes the fact that it's an integer. Because why? Because the definition of even is 2 times an integer. So every even number is an integer, okay? All right, if x is an even integer, then x squared minus 6x plus 5 is odd. Okay, let's see if we can prove that. So we're going to start with let x be an even integer. I'm going to write it like this. Let x be an element of the integers that's even, so we write it like this. I know if I said that in words, it would sound odd. I would say, let x be an element of the integers be even. I know that's not grammatically correct, but when you write it down, that is the way you would normally write it, because I can justify that by saying like this: let x in the integers be even. That's how I would say it to make it sound grammatically correct. Okay, now we need to figure out how to get from that first line to the last line, right? Let's take one step in each direction. From the top, we'll take a step down. Because x is even, what do I know about x? I know that it fits the definition of even, which is what? 2 times some integer. Okay? So I'm going to write then x equals 2 times something, where that something is an integer. And why do I know that? I know that by the definition of even. Okay? Let's go to the bottom and take one step up. What would allow me to conclude that x is odd? I can conclude x is odd if x fits the definition of odd. What's the definition of odd? A number that is 2 times an integer plus 1. So my goal is to get to this point. Then x squared, I may have said x a minute ago, and I didn't mean x, I meant this number that's there, which is x squared minus 6x plus 5. equals, hopefully, we'll be able to show that it equals 2 times something plus 1, where that something is an integer. Now, I'm not writing that in gray because I know this. Not at all. It's exactly the other way around. I want to know this. And I will know that if I can get to here. Because then I can say that that number is odd by the definition of odd. And then I'll be done with my proof. So the question now becomes, I don't have to worry about this anymore. Now I just have to try to get here. And technically you could start at the end of a proof and work your way all the way back to the beginning. I personally like to do this. I like to take maybe one step back from the end, just so that I have an idea of what I'm trying to get to. And the rest of my work, I like to go from the beginning and move forward. Some people like to do the same amount of work in each direction and meet right in the middle. You know, I usually do about 80, well, I at least think, at the beginning, I at least think about what does my penultimate line need to be. Penultimate means next to last. So I think to myself, what does my next to last line need to be? Maybe I don't write it down, but I at least think about that so that I have for myself a mental goal. And then I go to the front and try to work my way to that. If I can't figure out how to get there, then I go to that penultimate line and I try to figure out, okay, well, what will need to come right before that? You see? Okay. So anyways, let's go now to where we left off there on line 2, and let's figure out where line 3 is going to come from. Okay, so I don't know anything else about x. It's an integer that equals 2 times an integer. That's all I know. So at this point, I'm thinking about, okay, I should probably now start transitioning. I can't say anything else about x. So I should probably start transitioning to the number that they're actually asking me about, which is that number. Okay, well, I can do that, right? Because if x is 2a, then I can say something very important about x squared minus 6x plus 5. Can't I? Can't I say what that would be? It would be 2a squared minus 6 times 2a plus 5, right? I just used the substitution property there. This allows me to change this into this. Okay. Now, let's simplify that. What does that equal? Wouldn't that be 4a squared minus 12a plus 5? Now let's talk about what should you show versus what do you not need to show. You might be asking this question. You might say, could we have just said this? Could we have just said that? And the answer is yes, you could have. I personally think if you do that, if you go straight from here to here, I think that's too big of a leap. Not that it might not be true, but here's the overriding principle. Okay, remember, I don't remember if I said this earlier in this lecture or not, but remember that when laws are written, in the laws it always says, or usually says, a reasonable person. Okay? If you use violence to defend yourself against somebody, are you going to go to jail for that or not? They are going to ask themselves in court, would a reasonable person have been in fear for their life? And if so, then you probably won't go to jail. So when you're writing a proof, you have to ask yourself, would a reasonable person see what I wrote and have no questions? That's what you want to ask yourself. Now, I think to go from here to here, I think a reasonable person would have to stop and say, oh, okay, what did they do there? I got to figure this out. And if somebody has to stop and say that, then that means you haven't shown enough. Okay? Now, somebody who's not good at math might have to stop and think. You don't want to worry about those people. You want to worry about someone who is at the level that they can follow this mathematics. Okay? They might have to stop for a second here or there, but if they have to stop and really think, where did that line come from, then that means you haven't shown enough justification. And I think what I have underlined there in red, I think I think that you need that extra bit in the middle. So let's put that back where it was. You see, now there should be no question at all what's happening to anybody. Any reasonable person can look at that and say, oh, I see exactly what they did. They started with this, they replaced x with 2a, and then they simplified, and this is what they came out with. Okay? Now, what's our goal? Our goal is to make it look like this. 2 times an integer plus 1. So let's look at where we left off up there. Can you figure out how I can rewrite that so that it says 2 times something plus 1? How about this? It certainly equals 4a squared minus 12a plus 4 plus 1, right? And can't I factor out a 2 from here? And I think that's fine to go ahead and do that here. That's not too big of a step. So we're pulling a 1 away from the 5 to get the 5 as 4 plus 1. And we're going to factor out a 2 from those first 3 terms. That is not too much to do both of those in one step. So what would it be here? It would be 2 times 2a squared minus 6a plus 2. Okay, so let me write that down. 2 times 2a squared minus 6a plus 2 close parentheses. Okay? Well, now we can change that gray line to black. I need to change one small thing, but we basically got it. I wonder if I can just change the color without rewriting it. I'll be darned, look at that. What a fascinating modern age we live in. Okay, I do need to point something out though, right? All of a sudden this b shows up. Where'd b come from? You guys know, right? I've taken this number and I've just named it b, that's all. So what do I need to do? I need to make that clear. So I just said here where b is an integer, what I should really say now is I should really say where b equals 2a squared minus 6a plus 2, which is an integer. And there we go, done with the proof. Okay? Now, I do want to point something out. This is a pet peeve of mine when students do this part wrong. I mentioned this in the last lecture too, so I'm glad it came up here so I can mention it again. This is not 2 lines. Let's number the lines. Number 1, number 2, if you did this, 3, 4, 5, 6. Your numbering is not correct if you do that. There is not 6 lines in this proof. There's only 5 lines. Because that thing that I circled in red is 1 line. That is line number 3. Okay? You see, this actually belongs right there. It's 1 line. It's just that the line was getting too long and I was running out of room. So I took that bit, kind of like hyphenating a word in a way. Oops, darn. Well, there we go. And I just moved it down there. Oh, you might ask this question. Why way over there? Why didn't I put it right there? In fact, a lot of people do. This is just a personal thing for me. I just think it looks nice to have the equal sign lined up with the first equal sign from above it. That's all. That's just personal preference. It actually doesn't matter where you put that. I could have put it over here and lined it up with that equal sign. Or I could have said this. I'm going to put it at the beginning. Here's what I do a lot. This is another thing I like to do. You can say, okay, I'm going to put it at the beginning, but visually, I would like it to be obvious that this is not a new line. It is a continuation of the line above it. And so I do this a lot. I indent. Like that. That makes it clear. I haven't started a new line. I'm continuing a line. Okay? Now, let's read that out loud. It says, I'll highlight as we go. It says, hence, x squared minus 6x plus 5 equals 2a squared minus 6 times 2a plus 5, which equals 4a squared minus 12a plus 5, which equals 2 times the quantity 2a squared minus 6a plus 2 plus 1. That's the correct way to read that. Okay? That is really a smart way of condensing 3 lines into 1. Let me circle this again. What that really is, well, it's 3 equations, right? Why am I saying 3 equations? Because I see 3 equal signs. Each equal sign indicates an equation. What I've really done there, this is important for you guys to get. If you understand this stuff now, it'll just make life so much easier on you later. What I've really done there is I've really said this. Hence, x squared minus 6x plus 5 equals 2a squared minus 6 times 2a plus 5. And, I know you're not supposed to start a sentence with the word and, but I think that's a rule that we've kind of thrown out the window, so I don't worry about that. And 2a squared minus 6 times 2a plus 5 equals 4a squared minus 12a plus 5. Furthermore, for a squared minus 12a plus 5 equals 2 times the quantity 2a squared minus 6a plus 2 plus 1. That's the 3 equations. it could be written one equation per line, then I would have those 3 lines. But here's the catch. If I did that, I would need a 4th line in there because I need to show that this equals that. So I would then have to say thus, or let's say therefore. You don't have to use therefore only on the last line. You can use it in the middle of your proof too. Therefore, x squared minus 6x plus 5 equals 2 times 2a squared minus 6a plus 2 plus 1. Okay? So look. Those 4 lines have been very cleverly combined into one line. And that's the part that's written in red. That's one line that says these 4 lines. Okay? Now, just for the sake of, because I'm just trying to show you different ways you can do it, you could have done this. I could just erase everything before the equal signs. And then this is literally the exact same thing as this. Look at it. It is identical. Just that, in order to save room going to the right, I just did a line break. Now that is one long line. And because in that one line I have showed that this equals this, now I no longer need this. Do you see how that is? If you learn this stuff that I'm trying to teach you here at the beginning, it's not that hard. So many people say, oh, proofs are so hard. That's because they don't really put in the thought required at the beginning to really understand. So they're trying to learn how to do things without really understanding what's the difference between writing it this way and writing it that way. And so they go off on their own, unarmed with knowledge of what's the difference between writing something 2 different ways. And so, yeah, I'm not surprised that it seems hard because they don't really understand what they're doing. And that's why I'm spending so much time talking to you about how much you need to put in versus what's okay to leave out. And what's the difference between writing a line this way versus writing it another way? What's the proper way to combine 2 different thoughts in one line? I hope that's coming across. I'm trying to spend a lot of time discussing that with you. Because if you can understand that stuff now, then this will not be hard for you. And you will probably do very, very well in all of your other classes after this. Okay, now, I'm going to be honest with you. I stopped this recording because I found a mistake. And then I started a new one. So I made this recording in 2 parts. And because of that, I completely have no track of how long this lecture has actually been, because I don't know how long the first recording was. So I'm going to stop here. That's 3. Did we only did 2 proofs? Oh wow, I thought we did 3. No, I'm gonna pause for a minute and see how long this lecture's been. Maybe we have time for one more, I'm not sure. So I'm gonna pause it. You won't know that I'm pausing, but okay, it seems to me like we're probably up around 47 minutes, so I better stop. We'll do more in the next lecture.